So good morning everyone. So continuing the application of the biomedical signal processing. So next is the application of the biosignals to design multimodal assistive system. In the last couple of examples, we have seen that whatever the biosignals we are using, we were using only one assistive device. Okay, that means we are controlling only one assistive device using a generated set of control signals. However, what happens here when you talk about the life of a differently abled person or paralyzed person? In that case, if the person is say um, quadriplegic or paraplegic, okay, which makes them what you call bedridden, or they have to take the assistive help of the what you call multiple devices. Say for example, um, think of a person who is sitting on a wheelchair and he needs to control the movement of the wheelchair, and at the same time, suppose he is going to pick up something from a shelf which is much higher than he can reach. In that case, what might be the way out? Because if he is sitting on the wheelchair and he is not able to stand up, he will not be able to access the stuffs which are kept on the shelf or anything which is just out of his access reach. So in this case, one of the thing which has been discussed is that on the wheelchair, if we can fix a robotic arm. Okay, so say for example, this is the schematic of a wheelchair schematic diagram. I know it's not a very good diagram, but please bear with me. So suppose this is a wheelchair, okay, and if we attach say one robotic arm over here, like this, which can perform the additional work what the person wants to do, then it can help the person to a certain extent. Okay, but now if you look over here, what is happening? There are two independent devices. One is the wheelchair and the second is the robotic arm. Okay, so there are two independent devices which needs to be controlled. So how to control these? So such kind of system where we have multiple devices in a single device, they are regarded as multimodal assistive device systems. Okay, so in this kind of systems, as I told you, there would be more than one assistive devices which will be connected to each other to a control system. Okay, so in that case, say for example, herein we will demonstrate the activity or what you call how to control a multimodal assistive system using the EOG signal. So if you see, the vertical electrodes are there and then horizontal electrodes are there, they have been placed, then there is this reference electrode over there. However, if you look into the movement of the eyes, the movements of the eyes are very what you call are very restricted. That means you can generate only a certain set of movements in the eye. Okay, that means if you are having only a certain set of movements in the eye, that suggests that we will be having only a specific set of control signals. Okay, we will be having only a set of control signals. Now if you have to manipulate two independent devices using only a set of control signals which are limited in number, what to do? In that case, we can go for this switching devices, multiple switching devices. Say for example, if you see over here, there are two Hall effect sensors which have been put, Hall effect sensor 1, Hall effect sensor 2, and then there is this magnet. Okay, so if you bring this magnet towards the Hall effect sensor 1, then say it activates the wheelchair module. Okay, on the contrary, say you bring this magnet towards the second this Hall effect sensor, as in this case, then say it will initiate the controls for the robotic arm. Okay, so somewhere you need to include some switching mechanism into the system so that you can control the multiple devices. Definitely, you can also use the speech signals, just like in Alexa, what I told that Alexa do this. So what it does, it finds out the Alexa and then it activates the Alexa. Now, say you name wheelchair or robotic arm, and then you give the command. Then when you say the wheelchair will be activated, wheelchair control system may be activated through the voice, and then that control system concerning to the wheelchair movement would get the command. Similarly, if you want to move the robotic arm, then you can give the command robotic arm and then give the command. So robotic arm, when you speak that robotic arm is there, or you speak the command robotic arm, the robotic arm command based this control system, it would be activated, and consequently whatever the subsequent command you will be giving, that will be taken up by the robotic arm. So that is another way of doing that, but the simplest way is this instrumentation based systems where we can use the this Hall effect sensors as the switching mechanism. Okay, so let us take see the examples.
Activate. Activate. Forward. Stop. Backward. Stop. Forward. Stop. Left. stop, right, stop, backward, stop, forward, stop, Now the login is successful. I have to enter the contact details. Now I have entered the contact details, saving it. It's open up the primary telecommunication protocol. I'm starting it. Call. Now the process of calling has been started. Here you can see the incoming call. The status is showing the call is in progress. Now the call has been ended. Send SMS. It is showing the message has been sent. Here you can see the incoming message. That's the SMS by EOG. Now I will intentionally call the patient from an external mobile to his number. Now the user is getting a call, incoming call. Here you can see the status. Answer the call. Now the call has been answered and this is in progress. And the call has been ended from my side. Now I will once again make a call to the patient. Here is again the incoming call. End the call. The call has been ended. Now send email. Now the process of sending email has been started. Email has been successfully sent. We'll check the mailbox. Here you can see the incoming email.
So see, as I was telling you, in this case, what has been done? One robotic vehicle and plus communication model. It was used as a combination for the multimodal assistive systems. Okay. Now coming to the next type of one of the common methods for the analysis of the biomedical signals is the analysis of the ECG signals, because it is the most widely studied biomedical signal. Okay. Now, when we talk about this ECG signal analysis, we can perform the analysis in different domains. Some of the common methods, they include time series analysis, okay, frequency domain analysis, then time frequency analysis. It is also regarded as joint time frequency analysis in some books, JTFA or TFA analysis, then HRV analysis, and lastly RR interval signal based analysis. Now these HRV signals, they are also regarded as RRI signals. But you may ask why we have kept these two things separately. This is because HRV analysis, it is the analysis of the RRI signals which can provide us information about the autonomic nervous system. Okay. How many of you don't know autonomic nervous system? क्या है? Mm-hmm. Yeah, so kind of autonomic nervous system. It is basically uh, when we talk about the nervous system, there are two types of nervous system: central nervous system and the autonomic nervous system. Now, this autonomic nervous system, they are associated with two types of systems: sympathetic and parasympathetic. Okay, so just like yin and yang in the Chinese physiology, I hope many of you know yin and yang. So they are positive and the negative substances which tries to maintain the balance in the universe. Similarly, parasympathetic and the sympathetic system, they are responsible for maintaining the dynamicity within our human body. Okay, say for example, when we are trying to run, okay, so in that case our heartbeat increases. Okay, now what is bringing down the heart rate to the normal level? It is the balance of the sympathetic and the parasympathetic systems to maintain the basal level within our body by increasing or decreasing one of the parameters. Similarly, when we eat, we have muscles, say the gastrointestinal tract muscles, they are there, they are forming the muscles. So, how they will be acting, right? So, their action will be controlled by this sympathetic and the parasympathetic nervous systems. Okay. Then we talk about this dilation of the eyes. Who will maintain the dilation of the eyes? If you go into a darker room, our pupils, it dilates. That means its aperture increases. When we come to the bright light, its aperture decreases to accommodate the amount of the light which is falling onto the retina, right? So in this cases, who will maintain the balance within our human body? It is the autonomic nervous system which is maintaining the balance in our human body. Okay, so this is in the simplistic term what is uh, autonomic nervous system. Okay, I hope you will be studying in depth in the anatomy physiology class. Now, when we talk about this HRV analysis, it is basically a measure of the activity of the autonomic nervous system. Whether there is an increase in the sympathetic activity, whether there is a decrease in the parasympathetic activity, or whatever. Okay. On the contrary, when we talk about RR interval signal based analysis, it again can be directly classified into the time series analysis, frequency domain analysis, time frequency analysis. Okay, because other interval signals, what are they? They are nothing but time series signal. However, the RR interval is plotted against the time period. Okay, in the ECG signal, what we are having in the y-axis? In the y-axis, we are having the amplitude. Okay, that means the voltage that is being generated within our body. Whereas in RR interval, what is the y-axis? Y-axis is the RR interval between the two consecutive R peaks. So suppose over here we say the first RR interval at 0 second is say RR1 or say RR0. Then in the first second it would be RR1. Okay, second it will be RR2. In this way it would go. Okay, so RR0 is the RR interval between R0 and R1 peak. Okay, RR1, what would be the component? The component will be the time duration between the R1 and R2. Then what is RR2? It would be the time duration between the R2 and R3 peaks. Okay. So this is the basic difference between the ECG signal and the RR interval signals or HRV signals. Okay. So if I ask you that HRV signal or the RR interval signals, both are same. Okay. They are used interchangeably. HRV signals and RR interval, in short it is regarded as RRI signals, both are same. However, when we talk about HRV analysis, this means that you are trying to analyze the ANS system of our body. Okay. Now, why this HRV analysis is important? This is because, first of all, we all know, we have discussed previously that acquisition of the ECG signal is one of the easiest way to acquire any of the biopotential signal. Why? Because the amplitude of the uh, cardiac muscles, that is the ECG signals, it is much higher and in the synchronized fashion as compared to the any other biological signals. Okay, so that is the reason why the ECG signals has been analyzed across the globe by many of the researchers for different purposes. Okay, now since it is easier to acquire and that too in a non-invasive manner, so what it is allowing us, it is allowing us to analyze the autonomic nervous system in a non-invasive manner. Otherwise what happens is that most of the other methods for analyzing the autonomic nervous system, they are invasive in nature. Okay, you need to place the electrodes within the body. Okay, and you have to do the analysis of the chemicals at the certain sites. The analysis of this autonomic nervous system using the HRV signals, it provides us one of the easiest way to predict how our autonomic nervous system would be behaving. Okay, so HRV analysis is one of the much important stuff in biomedical industries pertaining to the autonomic nervous system activity. Okay, so these are some of the few applications of the ECG signal processing. Okay. Now, a typical ECG signal, it would look something like that. So you have, if you pick up any of these things, P, Q, R, S, and T. Okay. Again, it repeats P, Q, R, S, and T. In this case, if you see another peak, it can be seen after the A, T wave. It is U wave. Okay, but it is not much commonly studied. The reason being, in many of the volunteers, you will not find this U wave. Okay, so in classical textbook, you will find ECG segments as the P, Q, R, S, T. Okay, now from there, uh, how we get the RR interval? As I told you, say 0, this is R0, R1, R2, R3, and so on. So this is say RR0. This one it is RR1. This one it is RR2, and so on. So if you see, as the time progresses, we are getting certain points. See, there are a series of points. Okay, what are these series of points? These series of points are nothing but the RR intervals. Okay, and hence this signal RR interval, where we have the y-axis as the RR interval, it is regarded as the RR interval signals. Now the most important thing is that if you see the unit of this one in x-axis, time, seconds, in seconds, in y-axis, again we are having seconds, because RR interval, when we talk, what is interval? Interval is nothing but your time information, right? So in ECG it would be, see, amplitude, so it would be in millivolt, okay, whereas the x-axis would be in time in seconds. So please keep this in mind. We may ask you what is the difference between the other interval signals and the normal ECG signals. So we can ask you to differentiate in the examination. Okay. Now coming to the HRV signal analysis. So what we get over here, once we get this signal, if you see there is a trend line, this red line. Okay, what is this red line? This red line is nothing but the moving average of all the system, so that we remove some of the noise components, because when we smoothen it out, the high frequency components which are usually associated with the noise, they are removed, and we get a basal line. Okay, now this basal line is used for the HRV analysis. Okay, now how to do? We perform the this Fourier transform of that smoothened RR interval signal, and we get a Fourier transform spectrum. Okay. So can anyone tell me why we do the Fourier transform? What is the importance of Fourier transform? Mm-hmm. Time to frequency domain. Yeah, correct. So if you have any signal, say xt, and we are having any signal like this, so this is amplitude. If we perform Fourier transform, we would get frequency versus amplitude. Suppose from here, what is the frequency component of the signals? We don't know from here, right? Suppose this signal is made up of, say, 100 hertz, 200 hertz, and 300 hertz sine components. Now, in the frequency domain, we will be able to get peak at 100, 200, and 300 hertz. 300 hertz. Okay. Now, if you see in the HRV analysis system, where we are having this frequency component, we are having it as 0 to 0.4. Now you have to remember that frequency of the ECG signal, it varies from 0.5 to 120 hertz. Okay. Now why it is in the range of 0 to 0.4? The reason being, this frequency which is being plotted over here, it is a normalized frequency. Okay. Now you can see, after we have performed the Fourier transform, we are getting certain peaks over here. We are getting certain peaks over here. Okay. So what are these? These are very low frequency. Very low frequency. In the normalized unit, the frequency component would be 0 to 0.04 hertz. Then low frequency, it would be in the range of 0.04 to 0.15. So this is VLF, very low frequencies. This blue marked area, it is low frequency. Then high frequency, 0.15 to 0.4. So this red area, this is the high frequency components. Okay. So the whole of the spectrum, ECG spectrum, not ECG spectrum, the spectrum of the RR interval signal spectrum, they are broken down into three components, that is very low frequency, and high frequency regions. Then from there we can find out LF nu is normalized unit, LF component, that means the area under the curve under the low frequency in the normalized unit fashion. Then HF nu, normalized high frequency component. Then VLF percent, LF percent, HF percent. Then another important thing is that LF by HF ratio. Okay. Now this LF by HF ratio, it is a marker of what you call sympathetic or the parasympathetic dominance of the cardiac system. Okay, so from here, by the analysis of the LF by HF ratio, we can say whether there has been an activation of the parasympathetic system or an activation of the sympathetic system. Okay. Now, why this is so? Why we did not analyze the time domain RRI signals? The reason being, it has been found that frequency domain parameters, they can portray more clear picture of the ANS physiology. Okay, so if you have to understand the ANS physiology, then you have to convert the RR interval signal into its frequency components and then analyze the frequency components from there to have an understanding about the ANS physiology. Now coming to the time frequency methods, and there's some applications. So what are these basically? So when we talk about joint time frequency methods, there are several methods: short time Fourier transform, continuous wavelet transform, discrete wavelet transform, wavelet packet decomposition, Wigner-Wheeler decomposition, empirical mode decomposition, Hilbert-Wang transform. And these joint time frequency methods have been used for noise removal, arrhythmia detection, sleep apnea detection, biometric identification, emotion detection, epileptic seizure detection, driver distraction detection, and drugs and alcohol detection. Okay. Now, you would suggest, you may ask me, so why there is a need for joint time frequency methods, and what is the advantage it gives us over the other methods? The thing is that when we talk about any signal, when we are in the time domain, what is happening? So this is xt. In the time domain, we are having information about amplitude and time. But when you try to analyze any signal, a signal is constituted of three parameters: amplitude, time, and frequency. Now you would say, so just a few minutes back you told we can perform the Fourier transform and we can go to the frequency domain. So we will be having frequency and amplitude and we will be getting some peaks. Right? Now the thing is that, yeah, true. But over here you are only getting information about amplitude and frequency. In none of these, either xt or x omega, you are getting both all the three amplitude, time, and frequency components together. Okay, so if you are here, say at this particular instance of time, you will be able to know what is the time and what is the amplitude, but you will not get the information about the frequency. Similarly, when you come back to this frequency domain signal, over here at a particular frequency, what is the particular amplitude, you are getting the thing, but at what time this frequency is occurring, we do not have any idea. So this is what our, when we will be discussing about the joint time frequency analysis method, we will be discussing all the three. I don't think we will be covering this empirical mode decomposition, except this EMD, we will be covering the other methods, and we will see how the joint time frequency analysis, it allows us to locate the amplitude, the time, and the frequency of a signal. So these joint time frequency methods, they allow us in the localization of all these three parameters in a single graph, which is not possible in the conventional normal time domain and the frequency domain signals. Now you may ask, so what is the reason? The reason is, say for example, you have a signal, okay. If I plot the time and frequency here, so what would happen? Say from it starts from 0, there is a linear relationship. Okay, it is increasing. There is another signal. One common example is short signal. Okay, so at time 0, the frequency will be 0. As the time increases, frequency increases linearly. But there can be another signal which is regarded as inverse shift signal. What happens over here? At time 0, frequency will be maximum, and as the time progresses, you would find the frequency is dying down and it is coming to the 0 level. Now say this red line, it is having frequency component 0 to 100. The black line, it is also having frequency component 0 to 100. Right? It is also having 0 to 100 frequency component. Now, if you do, or if you perform the Fourier transform of both these signals, sharp and the inverse shift signal, what you would get? The Fourier transform of this one, for both the signals, they would be identical. Okay, something like this. Whatever, so frequency component is increasing. So, say whatever the frequency components, in both the cases, it will be same. Now, Fourier transform, it is a very good transform. Still, it is used, but the fallacy is over here. If there is a time varying signal, that means with time the frequency changes. So what it says, that from this frequency domain, it will get back, if we perform the inverse Fourier transform, we will get back to the original signal. But in this case, if we perform the inverse Fourier transform, to which signal it would map us? The sharp signal or the inverse sharp signal? So herein the Fourier transform, it fails, and hence there is a requirement for this joint time frequency method, analysis methods, which can help us in reconstituting the signal in a more efficient way. Okay, because if you remember in the first class, I told you, even if the ECG signals, they are considered as the rhythmic signals or the periodic signals, they are not periodic signals. Leave alone the other type of the signals. Okay, all the signals which are being generated by the human body, they are non-stationary signals and aperiodic signals. Okay. Now, I told you that all the signals are aperiodic signals. So how can they use Fourier transform? Fourier transform किसके लिए यूज होता है? Which signals can be analyzed using Fourier transform? Only the periodic signals. Anyone else? He says Fourier transform can be used only for the periodic signals. Any other answers? No. Usually Fourier series is used for the periodic signal analysis. Fourier transform, it is used for the analysis of both periodic and the aperiodic signals. Okay. Now, why that is so? Usually, you will find that many students, they will say Fourier transform, they are used for the aperiodic signal analysis. Now, why that is so? That is so because it is considered that any aperiodic signal, they are periodic in nature as time t tending to infinity. Okay. So because of that reason, so we start with this assumption, and because of this reason, many students, they say that they get confused over here, and they say that the Fourier transform can be used only for aperiodic signals. But the thing is that if something is periodic at t tending to infinity, say for example the periodic signals, sinusoidal signals, if it is periodic, say it is periodic at t tending to infinity, it is also periodic at a smaller distance also, time frame also, right? So if it is periodic at a smaller time frame, it would be periodic at t tending to infinity time period also, right? On the other hand, if you are having a aperiodic signal on a smaller time scale, it is not periodic, it is aperiodic. Whereas we are assuming that at capital T tending to infinity, it becomes periodic. So, though we are assuming that we are using it for the Fourier transform for the aperiodic signal, we start the derivation with this condition. But the fact remains that the periodic signals are also periodic at t tending to infinity. So due to this reason, Fourier transform, it can be used for the analysis of both periodic and the aperiodic signals. However, it fails to analyze effectively the non-stationary signals. What are non-stationary signals? The non-stationary signals are the signals which changes their frequency component with time. Okay, it changes their frequency component with time. And as I discussed with you few moments earlier, that all biomedical signals, they are, you cannot predict what would be the frequency in the next domain. So all the biomedical signals, they are non-stationary signals. Stationary signals, they have a fixed frequency. In other words, you can say periodic signals, they are stationary signals, whereas the signals which changes their frequency over the period of time, they are non-stationary signals. So all the biomedical signals by default, they are non-stationary signals because there is a dynamicity within the signals which are being generated. Okay. So this is how a short time Fourier transform it would look like. So what is short time Fourier transform? So if you see, we have given L equals to 2, L equals to 2, L equals to 9, L equals to 18. So what are these? These are nothing but what the short times Fourier transform says, that we will prepare, get a window like this one in the time domain. Okay, we will extract the signal component, we will perform the Fourier transform. Again, this window, it will be moved to the next side. So in the next stage, this signal component would be extracted, and then we would again perform the Fourier transform. So in that way, what is happening? So this is your, say, time, this is the frequency. So at particular time, what is the frequency component you are able to see, and what is the amplitude, it is shown in the z-axis with color information. Okay, so over here you are getting all the three components: time, frequency, and the amplitude. Okay, however, if you see, when L is equal to 2, the window is very short. So if you see, when time window is very short, we are losing the frequency information. When we are increasing this time window slowly, you can see we have got some good results over here. This analysis, if you see this analysis over here, again when we further increased, there is a some reduction of the quality of the image what we have got. Now why it is so? When we have to keep it in mind that frequency is inversely proportional to time. Okay, when you are making t very small, say for example tending to 0, then your frequency it is getting a value of infinity. That means we are losing the time information, frequency information. However, when the time is very large, when we are taking say a longer period of thing, so what would happen? Your frequency resolution will again, sorry, when your time is short, your frequency resolution is lost and time resolution is increased. If you see within a short time, you are getting a very good spectrum. However, at a longest time period, your time resolution it is being lost. However, your frequency component, if you see, it is restricted up to 20 hertz. Okay, whereas if you see, it is more than 20 hertz and you are getting spike like thing. So somewhere we have to come to an optimum result. In this case, the optimum result was obtained at L equals to 9. So if you see, neither this one, the first one, neither the third one, they are giving you a proper result. However, you can get some meaningful results which is in between the first one and third one, and that can give you some important information. Okay, so whatever the window period you will choose, it would be associated with some frequency component, and either there will be a very good frequency resolution or there will be a very good time resolution. However, you have to contemplate both the things and you have to come to an optimal position where you get optimal frequency and time resolution, and from there you can go for the analysis. Okay. 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 Okay, we are coming to the wavelet transform, so I will discuss it in the next class. Do you have any questions?